Hello and welcome to Lecture 6 in Transformation, Semigroups and Applications. I am Dr. A.T. Imam, a lecturer at the Department of Mathematics, Ahmadu Bello University, Zaria. In this lecture, we are going to talk about height and defect of a finite full transformation. So let Xn be a set of 1 to n elements, a finite set of n elements, and denote by Tn the full transformation semigroup on Xn. Recall from our previous discussion that for each alpha in Tn, the image and the kernel of alpha are respectively given by Im alpha is a set of all points in Xn such that there exists some x in Xn such that x alpha equal to y. So any point that has some pre-image under alpha is an image point and is denoted by Im alpha. The set is denoted by Im alpha. And the kernel of alpha is a relation on Xn defined by the rule that 2 points x and y are related if they have the same image under alpha. It is clear from the very definition of the image and the kernel of alpha that if one take two finite full transformation alpha and beta in Tn, then the image of the product is contained in the image of beta, the second factor. So if you multiply, if you compose two maps, because we are composing from left to right, so what we are doing is applying alpha first and then beta. So at the end of the day, the image of the product will be picked from members of the image of the last factor. So therefore, Im of alpha beta is always contained in Im beta. Likewise, if you look at the definition of the kernel of the product will also be a superset, will contain the kernel of alpha, will be a superset of the kernel of alpha. This is because element may be related, element that are related under kernel of alpha will remain to be related in the product. But you can have 2 points that were not related on the kernel of alpha, but because they are related under kernel of beta, so eventually in the resulting composites they will be related, meaning having the same image under the product. And so therefore, kernel of the product contains kernel of alpha, that is kernel of the first factor. So if you compose any two finite full transformations, the kernel of the composite will always contain the kernel of the first factor. This is because of the way we perform composition of mappings. We compose from left to right. So we define the concept of height of alpha. Now, given a finite full transformation alpha in Tn, the height of alpha is defined to be the cardinality of the image set. It is denoted by h alpha. So this is an integer associated with every alpha in Tn, and it is called the height of alpha, denoted by h alpha, and it's nothing but the number of elements in the image set of alpha. But then in our second lecture, we already said that every map can be written in the array form as the kernel relation here will partition the set Xn into equivalent classes, where they group a particular class, which we call block of alpha, is a set of all elements with having the same image. So therefore, the number of kernel blocks, or the number of elements in the partition of Xn by alpha will be exactly the number of images. And that is why height of alpha is also equal to Xn by kernel of alpha. So to look at a property of the kernel of alpha, we immediately observe that if alpha and beta are elements of Tn, then the height of the product will be less than or equal to the minimum of the height of alpha and the height of beta. So in other words, if you compose any two maps, the height will always go down. So you cannot have height of a product being greater than height of any one of the factors. So the height of the product is always less than or equal to height of the factor. If you look at our example, our equation 1, where we said over here, we say the image of the product is contained in the image of the second factor. Likewise here, the kernel of the product contains the kernel of the first factor. So actually, one will immediately observe that the height of the product is less than or equal to the height of the last factor of the product, because image of alpha beta is always contained in the image of beta, and so therefore the cardinality of the image will be less than or equal to cardinality of the image of beta. And likewise, by the same equation, one will see that height of alpha beta is equal to xn by kernel of alpha beta, and then this will be less than or equal to the xn by kernel of alpha. This is because you have a bigger set here. Actually, this is kernel of alpha beta is bigger than kernel of alpha. So you can think of it as if you are dividing x by a smaller set, and so therefore the quotient will be greater. So when you divide by kernel of beta, you have a bigger quotient, and so therefore the cardinality here will be less than or equal to the cardinality over here. But the cardinality of xn by kernel of alpha is equal to the height of alpha. So therefore, in both situations, one sees that height of the product is less than or equal to height of any one of the factors. And so therefore, we have the claim of the lemma here. So the height of a product is always less or equal to the minimum of the height of each one of the factors. With this, if we write for each r from 1 to n, jr to be the set of all alpha and tn that have height equal to r, then we see that tn partitioned into classes, into j1 union j2 union jn, because you cannot have an element with two different heights. This height is a unique integer associated with every element, and so therefore an element cannot be in two different j sets, j classes over here. And so therefore these are element of height 1, and these are element of height 2 up to element of height n. So and height cannot be beyond n, because you have only up to n element in the set, in the underlying set. So the number of elements that can be in the image is at least 1 and at most n. And so therefore tn partition into these n classes. And this is actually giving tn a nice structure where you can order these j classes. This j1, you can think of j1 as being less than or equal to j2. You have a partial order naturally defined on these j classes, and so therefore you can arrange the layers, tn in layers. So where this is a group of all element of height 1, group of all element of height 2, and you have element of height r up to height jn. And then you can also think of by this particular lemma, one will see that if we write knr to be equal to the set of all alpha and tn of height less or equal to r, then by the lemma 2 here, knr is an ideal in the sense that product of any two elements. Well, first of all, one will see that by the lemma it is a sub-semigroup, because whenever you multiply any two elements in this knr, the result will still remain to be in knr. And even if you take an element, if knr is from here down to the last, so if you have knr to be this portion of tn, then if you pick any two elements, the product will be of height less or equal to minimum of the two. And so therefore the product will remain to be there. Even if you pick an element from up here, and multiply with any element down there, you will still achieve the product to be within KNR. So KNR is an ideal. Of particular interest will be KNN minus 1, which is equal to which is donated by SINC-N. SINC-N is actually this portion of Tn. So from Jn minus 1 down to J1. So what you are doing here is you are removing the permutations, that is element of Jn. Jn is actually the set of all permutations, because these are elements with exactly n point in the image set. And this will be permutation. So, and apart from permutations, elements in Tn are not invertible, so therefore you have a singular part of Tn and it is donated by SINC-N. Now we define the defect of alpha in Tn. So the defect of alpha in Tn is defined to be the cardinality of xn minus m alpha. That is, apart from the images, the element that do not appear in the image set, their number is what we call the defect of alpha, and this is now n minus m alpha, or n minus the height of alpha, because if you remove the images you get the defect. So therefore n minus the height of alpha will give you the defect of alpha. It can be observed that the defect of a product is always less than or equal to the sum of the defect, and this can be seen from the fact that if one pick an element that is not an image point of the product, then that element is either not an image point of beta, or it belongs to this particular set. We can visualize what we are saying here. If you have the domain of the product, since we are talking about full transformation, will consist of all finite of the entire xn. And so therefore, in the composite, alpha will first map an element of the domain to the image, which will be eventually mapped to the image here by beta. So x alpha will be mapped to the image here by beta, and then so we have the image of the product is always contained in the image of beta, as we have said earlier, and then it's actually this point that belong to the image of alpha here that will eventually map. So the point that intersects the domain of the image. So beta will take every point here to a portion, but an element here that is mapped outside of the image will outside of the image of the product will not be part of the image of the product. So if you pick a y, what we are saying here is if you pick a y from outside of the image of this product, that y may either be here or it may be a point here. It may be a point here, a y. And so therefore, if it is here, then it means it is outside the image of beta. And if it is here, then that y is in the image. It will be an element of the image under beta, but of a point coming from outside of the image of alpha. So it has to be an image under beta, but of some point out of the image of alpha, and that is why you have this kind of two cases. So which means this particular set, the defect of alpha can be partitioned into this or that, and it is always the case that this thing is a disjoint union. And so therefore, with one extra observation, that this set is always less than or equal to this particular set. Yeah, because this is the image. So actually this is the image. This is part of the non-image point of the image of beta. So this is a part of the image of beta, and so therefore it is less than or equal to xn minus m alpha. We can see it from here that because this is a portion, if you look at the images of this set here, It's actually referring to this portion of